So today I'm going to review magnetostatics, and we're going to look at it in terms of the equations and how they can be used for modeling electric machines. So we have Amperes Law. And this is, I'm going to continue using the equation numbers from the last lecture. So this is the current density enclosed within a surface. So if this can be simplified to just enclosed current. So if you have a wire with current flowing through it, and you integrate the magnetic field around some closed loop, then the value of that line integral will equal the current flowing through it. But in this form you can have a more complicated current. It could have a cross-sectional area. And then, so this is the integral form, and then the differential form of this is del cross H equals J. And then we also have that if we integrate the magnetic flux density over an enclosed surface, then the total where this loop means it's enclosed, the total has to sum to integrate to zero. So if you have a magnet and you had an enclosed surface, then this is just saying that the magnetic field going out of the enclosed surface must equal the magnetic field going in. So this is for a closed surface. And then the differential form of this is del dot B is equal to 0 if you convert this into differential form. So 11. So this says that total outward flux through any closed surface is 0. But if the surface isn't closed, then this doesn't have to be 0. So if surface not closed, if I didn't put this little circle indicating it's closed surface, then if you evaluate the field over just some surface, it doesn't have to equal 0. It's the flux. For example, if we had the magnet and we wanted to know the field over this surface, that surface is not closed. It's not completely surrounding the source. So the field going through that surface, the flux going through that surface does not have to equal 0. Right? Okay? Any questions on that? Okay, so this is just a review. So then now if we look at, so this is for magnetostatics, so there's no current. So there's no changing field. There can be current, but it has to be constant. So if we look at 12, we need to have that the del dot B equals 0. So this is the differential form of saying that the field can't spread out without closing on itself. That's why it has to be equal to 0. So now if we recall from vector calculus that so if we have del dot B equals 0, if you look up for vector identities, you can rewrite B as del dot del cross A, and that has to equal 0. So if you compare del dot B and del dot del cross A, cross product, you can note that these two are equal to 0, and so therefore we can define the magnetic flux density in terms of A, the magnetic vector potential. So we call A the magnetic vector potential. And so it turns out that A is often easier to calculate than B. So why bother making it more complicated looking? Del dot B looks pretty nice. This equation clearly looks more complicated. But if you if you take, for example, a 2D problem, so if you had a 2D problem where you only have magnetic field in the x and y axis, okay? So note for 2D x, y axis problems, only bx and by fields exist. So then if B only has x and y, then if we write this out, we can find out that A only has to have one term. So if only Bx and By fields exist, we only need one A component, since so if we write this out, thanks, shut the door. So if we write out this cross product, then so when we only have if we only have a 2D problem, then we only need the AZ term, the Z component of A, because if we then evaluate this, so if we take down the X term, then we get del AZ del Y and then there's no second term, so that's x, and then the y term is yeah, that's right, and then the y term is del az del x with a minus because it's the middle one. So we have minus del az del x y vector. So what this is telling you is if you can define your problem, if you have a 2D problem and you want to know what the field is in the x and y directions only, then if you solve your problem only for AZ, only for one component, you can then determine what the magnetic flux density in the x and y direction are. So this is really useful because it's a lot easier to solve one term than two. So you first formulate your problem in terms of AZ, you find the value, and then you can at the end post-process and calculate what Bx and By is. Okay. So let me just write that. So the AX, AY components are not needed to model fields in 2D. So okay, but what is this magnetic vector potential? What does it mean? So some people say it's just a mathematical tool to approach to use to calculate B, but I think the best way to think about what A physically means, because there is no magnetic vector potential meter. You can't buy a meter to measure that directly. It's a term that's used primarily for calculation purposes. But it does have some physical meaning. So this is how I think about what it means. So what is A in physical terms? We can't measure it directly. Okay, so now, so if you think about flux, so over some surface, so again, let's take this magnet example here. So we have some surface here that we want to know the flux of. Okay, and so and this surface here has a boundary on it. It's a rectangle, so the boundary has a path L. Okay, so then so now we know that B is related to A by del cross A is equal to B. So let's substitute 13 in to the flux equation here. So then we have del cross A like that. Now we can we can actually use Stokes' theorem. So this is a surface, not a closed surface, it's a surface. So we can use Stokes' theorem to transform this into a line integral. So then this becomes a line integral where we evaluate A dot dl around a loop. And that loop that we evaluated around in this example here is the edge of this rectangle. Okay? So, and this has, and so A, the magnetic vector potential, what's the units of flux? Anyone? We're on camera here. Weber, right. So the units of magnetic vector potential, flux is Weber, Webers per meter. Because if you divide by the length. So A has units of Weber per meter. But so think about this. This means you can calculate the flux by evaluating a surface integral. This is this is a double integral here. I've written it only as an S. This is an area. So we evaluate a surface integral to get the flux, or we could calculate the flux using a line integral, where you only have to evaluate one integral, but we have to evaluate that around the path. So the way I think about it is that this is a kind of convoluted. This is my best answer for what the magnetic vector potential is. It's the magnetic vector potential gives you the flux around, if you evaluate the magnetic vector potential around a loop, it'll give you the flux. So that's the best physical answer I have to what that is. Let me write that down. So the integral of A around a closed loop L gives flux flowing through loop. Okay. So now that this gets interesting if you think about a 2D problem. Okay. So in this example here, it's got a, if we define the coordinates like this, x, y, and z is into the page, then you've got the four sides of the rectangle, right? With a 2D problem though, you just have a surface. So let's think about that for a minute and what that means. So for 2D xy axis problem, 2D Cartesian. Now if we redraw the loop a bit more clearly here, like this. So we have x, y, and z. And so this is D. This would be D into the page. So if you have a 2D problem, you just have some defined depth. It could be 1 meter or 0.1 meter or whatever. But it's not a 2D problem. The values do not change as a function of depth because it's 2D. You only have x and y. It's only a surface. So, but for flux, if we evaluate if you think about it from the magnetic vector potential, then the flux flowing through loop L is it's going to be AZ dot DL. Well, let me write it in terms of A. We've got A dot DL. That's the most general, right? But A only has an AZ term, right? So, so we only have AZ. So if you evaluate it around this loop, what would be the value going along what would be AX going along the X direction? There is no AX. This is 2D. We only have AZ. We only have an AZ term going into the board. We don't have an AX or an AY term. So there is no value of there is no AX. But we do have an AZ. So we have an AZ at this point, and we'd have a different AZ perhaps at this point. So there's different AZ terms on the surface of the problem, but there is no, if it's a 2D problem where we only have to solve for Bx and By, we do not have an AX or an AY. So we only have an AZ. So then for this problem then, the DL, the line integral, you would evaluate it along the DL and would have an X and a Z term, right? DL is equal to dx plus dz. Now, like I just said, there's only a Z term for the magnetic vector potential. So then if we evaluate the dot product of these two vectors, we will, because there's no Z term, there's no X term, then Z dot X is equal to 0, right? So we end up with just AZ dz. So therefore, this integral then becomes an evaluation of the difference between AZ1 and AZ2. And actually, I think it's important that you understand this. So I'll write down the answer, and if you can talk to me if you don't get it. So we'll end up, if you evaluate this, we'll end up with AZ at 1 times the depth minus AZ at 2 times the depth, or I can write that as AZ1 minus AZ2. So think about this for a minute. If we want to know the flux, consider a problem here where you have a magnet, okay? Or you could have a winding or other problem. You want to know the flux through a surface, okay? But it's a 2D problem. So you draw the surface would have some depth, but since it's a 2D problem, it just becomes a line. Now you want to know the flux through that line from that magnet. in order to calculate that flux, all you have to know is what the magnetic vector potential is at the 2 points and subtract the difference, and that will then give you the net flux flowing through that surface. So it's really quite useful, because then you can then, for example, flux is very useful because you can then, if you take the derivative of that, you'll get the voltage. So this is a way of, in 2D, you can easily calculate flux from just evaluating the vector potential at 2 points. Okay, any questions? Does that make sense? So you don't have, in 2D, you only, because it's only got a bx and a by, you only have the z component. And so therefore, if you were to evaluate the integral around here, along this path, along this depth, the AZ2 can't change, right? Because it's a constant. It's a 2D problem. Along this line, there is no AX. Along this line, there is no AX. Along this path, there is only one value, because again, it doesn't change with depth because it's a 2D problem. If it's a 3D problem, then you'd have to evaluate all the way around. But a lot of problems and a lot of problems can be modeled using 2D with pretty high accuracy. So this is a really useful result. So think about this if you don't quite get it. Okay. I think I did. Let me just write. Let me just try to make it totally clear for you. There is, in 2D, there is no contribution of path in x direction since dot product of AX is equal to 0. Okay, so moving on now, we'll take a break in 10 minutes. So let's now think about if material is present. I've been using this magnet example, but now let's add the equations for material. So if material is present, then we have that the magnetic flux density is related to the magnetic field intensity by this magnetization vector. So this is that vector is a property of the material from magnetic material, and then H at a particular point would be from some source. So if we look back at 10, equation 10, so if given that, and for magnetostatics, we have del cross H is equal to J. That was 10, and this is 15, right? This is 15. So we can rearrange 15 and substitute it into 10. That will then give us, so 15 into 10, we'll then get del cross B divided by mu naught minus M is equal to J. So that's 16. And now, now B can be rewritten in terms of the magnetic vector potential. So we can substitute 13 into 16, and then we'll get del cross A divided by mu naught minus M is equal to J. And I'll call that 17. Okay, that's looking messy. But now we have del cross A. So if we look up vector identities, so using vector identity, we can have del cross A is equal to del dot A minus del squared A. That's just a vector identity. So that we've defined B as in terms of A, but we haven't, and so we've defined the curl of A, but we haven't defined the divergence of A. So we can as long as A always satisfies the conditions of B, we can actually choose A to be the simplest possible. So the simplest possible value for the divergence of A is 0. So, and that's called the gauge condition, the Coulomb gauge. So if we choose the Coulomb gauge, which is del dot A is equal to 0, then this term here in this identity will be 0, and that means that this del cross A can be replaced by del squared A, which is a lot easier. So that gives us so 17, equation 17 then becomes minus del squared A divided by mu naught is equal to del cross M plus J, and that's equation 18. So these two terms here are the source terms. We have magnetization vector and a current vector, current density. So these are source terms. So if you look back at the very first equation, I had written an operator acting on an unknown is equal to some source terms. So now this is the source. The operator is this, the del squared over the mu naught, and the unknown is A. So we need to figure out what that A is. Okay. Okay, let me continue a little bit. So okay, so I'll just do one little bit more and then we'll take a break. So what happens now if we have a problem without any questions on this? Everybody doesn't want to say anything because they'll be recorded on camera, perhaps. This should be maybe you saw a lot of this in the fields class when you took fields, but we're looking at this from a somewhat different perspective. Okay, so now if we don't have any source terms, then things simplify. And so you might say, well, that's very silly. Why would you'd never have? I mean, if you don't have any sources, then it's not of interest. But what you could have is you could have a bunch of magnets, and then around it is air. So then this would be one subdomain, and then surrounding it, maybe another magnet's not a very good example. Maybe it's an actuator, a moving actuator with a magnet in it, say. So this whole region here could be one subdomain, it'd probably be multiple subdomains within that one. But then you'd have an outer subdomain with air. So then in the outer subdomain, there is no source. So in this subdomain, you could model the problem using more simple equations, and that's what a lot of programs do. So let's just think about how you'd solve problems if you had air in certain regions. So in that case, the source terms would be 0 in those source-free regions. So magnetostatics with no current. So if we go back to Amperes Law, equation 10, if we look at that, if J is equal to 0 in a region, then from Amperes Law, we have that just del cross H is equal to 0. Okay, but then, now if you look up in the back of a book, vector identities, you can note that we know from vector identities that del cross del phi is equal to 0, where this is the gradient of some scalar equation. So if we compare 19 and 20, we can say, hey, H is a vector. That means you have to solve for 3 unknowns. Phi, that's a scalar. Maybe it would be a lot easier to solve one thing than 3, and then you could then determine what H is by taking the gradient of this phi. Okay, so that's the idea. So phi is a scalar. So if we compare 19 and 20, we can say that the magnetic field intensity, H, is equal to the gradient of this phi, which is called the magnetic scalar potential, or the scalar magnetic potential. So then B would be mu naught H. Oh yeah, that's right. This minus here is by convention. It then matches the electric scalar potential. So then we'd have B. We could determine the magnetic flux density from H. If it was in air, it would be mu naught here, and then so we'd have minus mu naught. If I expand this out, this gradient will have del phi del x plus del phi del y plus is in the y component plus del phi del z is the z component. I don't know if I said, but I'm using the convention that that if I put a hat on it like this, that's a unit vector. So it's only pointing in the x direction. So it would have a value of 1 in the x direction, and it's got a value of 0 in the y and z. If I wrote with a line on it, that would be confusing, but that would mean, because I've got x for both of them, I try not to do that. But if I use A, for example, put a line on it, then that's a vector with 3 components, x, y, z. So here, for example, B is a vector with an x component, a y component, a z component. So by solving for this magnetic scalar potential phi with the problem, then you could then determine what the magnetic vector potential was by taking the gradient of phi in the location you're interested in, knowing the value of B. So let me just write a little bit, and then we'll take a short break. So phi is called the scalar magnetic potential. I actually like calling it or magnetic scalar potential. I'll use that term. And it's not always, that variable is not always used, phi. Sometimes Vm is used, or omega is used for the magnetic scalar potential. It doesn't have it's not like B is for magnetic flux density is always used. Now this magnetic scalar potential is another thing you cannot physically measure. It's a useful mathematical approach for allowing us to solve problems when there's no current. So it's not something you can't buy a magnetic vector potential meter either. But again, it's really useful because you only have to solve for one unknown rather than 3. And the negative, that means negative sign is convention. This negative here is based on convention. It agrees with electrostatics, since E is equal to minus del V, the electric scalar potential, which is a physical thing that you can measure, the voltage, right? And one more point is, as far as I know, all commercial, mainstream, magnetostatic, FEA, finite element analysis programs use the magnetic scalar potential in problems where there's a lot of air region rather than B. In the subdomain. Now, but this is for 3D problems. This scalar potential is useful. So because so I'm talking about for 3D problems. If you have a 2D problem, then you can just use for the 2D problems, you just where you don't have the Z component. Here, you can solve instead using the magnetic vector potential AZ. So the whole problem can be in terms of AZ. There's no real benefit using the scalar potential. Scalar potential only has one term. AZ only has one term. So in 2D problems, AZ is generally used. So the magnetic scalar potential is really useful for 3D problems. Note for 2D problems. Often, normally use AZ. I should say there are other programs that use different formulations for the fields, but this using the magnetic vector potential is the most dominant. That's from my experience and understanding. Okay, so we'll take a break and then we'll come back. Okay.